So yeah, I'm Nicholas. I got my PhD from Berkeley under Dave Wagner a couple years ago, and I'm now at Google. And I'm going to talk about some work that I've been doing with many others, looking at privacy-preserving machine learning. So I should say this is work with a bunch of people, and many of them deserve most of the credit. But I get to talk to you. So the general setup for this is something like this. We have some images and we want to train a machine learning model to make it classify them well. These are images from CIFAR 10, which is one of the standard machine learning benchmarks. And the idea is that we want to make sure that given direct access to this classifier, it's not possible to pull out individual images. For CIFAR images, maybe I don't care if it's possible to pull out this image of a horse, but if this was trained on medical images or people's text messages, you can see how it would be problematic if it would be possible to fairly easily pull out individual images of specific people. And so the general setup for this is how can we train classifiers with this property? And there are techniques that are provably correct, like differential privacy, but they're slower and less accurate. And so the question that researchers have started to study recently is something called privacy through instance encoding. And the way it works is instead of taking your standard images and feeding them into the classifier, what we're going to do is we're going to turn them into encoded images. And these encoded images are going to look essentially like noise to all of us, but are going to have the property that you can still train the classifier on them, and it will still be accurate on the original images. And it's kind of magic that you can do this, but you can't. Like, you can train classifiers on these noisy images, and it turns out that as a result, the classifiers still receive almost exactly the same original accuracy. The question is, are they private? So you can make the argument that because the data set is private, then any learning algorithm trained on top of it is also private. So these images here, like, to us, we can't inspect them and see anything interesting that reveals actually the training data that actually is these images here. And so the hope is that because this data set has been made private, it doesn't matter what algorithm you train on top of it. We're learning on top of a private data set, and therefore we are going to be learning something with privacy. So the question is, how private is this actually? And this is what I enjoy doing, is analyzing these kinds of systems to see how strong they are, and is most of what I did when I was a grad student at Berkeley. And I used to do it on, like, almost exclusively at generating adversarial examples, and now I've started trying to attack other systems too. And this is the most recent one that we've been doing that I think is a lot of fun. So in this talk, I'm going to focus specifically on a proposal called Instahide. This is some work out of Sanjeev Arora's group, which was published at ICML, and is the leading approach for how you might do instance encoding to preserve privacy. You can tell it's the leading approach because it just won the second place in the 2020 Bell Labs Prize. And so, like, people really believe that this is a strong method that is going to offer privacy. So let me briefly tell you how Instahide works. It's a relatively simple approach, and it has two pieces. So first, we assume that there's a private data set. These are images that I think of as sensitive. Maybe for this talk, these are images from CIFAR 10. And for some reason, I'm going to consider them sensitive. And I also have a public data set of images that are not sensitive, that are just random images scraped from the internet or something. Here I'm showing you images just from CIFAR 100, just to have a different distribution. Now, the way Instahide works is I'm going to choose a couple images from the private data set and a couple images from the public data set. And then I'm going to add them all together, so sort of like taking the pixel-wise average. And that gives me sort of this blurred image. And now I'm going to take this blurred image, and I'm going to randomly flip the sign of some of the pixels to be either positive or negative. And this gives me this resulting noisy image. And this image has lots of noise, and we probably can't learn on it by itself. But we'll put it aside, and we'll repeat this process all over again. I'll get two new private images, two new public images, put them together, flip the signs, get another noisy image, and we repeat this process many, many, many times until I end up with some big, giant encoded data set. And now the claim is that you can release this encoded data set into the world, and anyone can train a machine learning model on this encoded data while making sure that you've now preserved the privacy of the original images. This is what Instahide tries to achieve. And so what we are going to do is we are going to analyze Instahide and try and understand how private this actually is. Okay, so how are we going to do that? Because I only have a few minutes, I can't tell you exactly what we do, but I can give you almost like the idea of why you should believe this is possible. So in particular, what I'm going to try and do is I'm going to try and just directly convert from encoded images into these original like other images, essentially like decrypting them, if you think of the original process as some encryption algorithm. So our attack has two steps. The first step is to take a bunch of the encoded images, all of the ones that we've been given, and we're going to cluster them into images so that each cluster has only images that share one of the encoded images. So that what I mean to say here is every encoded image has two private images that went into it. And so each cluster is going to contain only encoded images that share one of the original images that went into this. And then, given those clusters, we're going to somehow go and take each cluster independently and recover the original image that was used in each of those clusters. So in a little more detail, you can think of what we're doing is I'm going to try and have some function, f, that can predict if two encoded images share at least one original image. So in this case, the answer is no. The classifier should output 0, this function f, because these four images up top are different. On the other hand, if these two images were shared, then this function f should return 1. And so it's going to predict whether or not there's an image shared, and we're going to try and figure out some way to do this. And the observation we make is that we're already training, like these encoded images were designed to be able to have machine learning algorithms right on top of them. That was the purpose of creating them. And so what we're going to try and do is we're just going to train a new machine learning algorithm to predict if two encoded images have any image shared in common. And we're just going to train a classifier to do this. Like I don't know how to write a program to do this very well, but because we know that machine learning algorithms can already be trained on these encoded images, we're going to do the same thing. And we're going to train a new algorithm to predict this separate task, which is different than the original task of classifying them. Now is just doing this prediction task. And once we have this classifier that can return 1 or 0, then this lets us go and construct a graph, where we have a graph that says which images are similar, and there's an edge between each pair of images that we think are similar. And now what we try and do is basically find the densely connected components. There might be some errors. Maybe there are going to be some spurious connections in here because our classifier might not be perfect. But if we find the densely connected components, then this corresponds roughly to one cluster per original image that went into the algorithm. Okay, so now we have these clusters. What do we do with them? All we're going to do is we're going to take them essentially one by one and use them to recover the original images that we used here. And the way we're going to do that is in practice a little bit complicated. There's some big matrix we compute and we take the inverse and do some fancy things. But the way you can think of it is imagine that we took all of these images. We know that each image by itself is very, very noisy. But we know that they all share one original image in common. And so if you were to put them all on top of each other and sort of just take the pixel-wise average, you would get a reasonable approximation to the actual original image. And you won't get the actual original image because there's noise here. But just by taking the average, you can get a reasonably good approximation. And by doing something a little bit more careful, you can get a very high quality reconstruction. Okay. So how well does this attack do? We actually implement this in practice. And in order to attack something, we attack the Instahide challenge, which is a challenge that the authors released. and they said, we think our scheme is secure. Here's a data set that's been encoded. Please try and attack our data sets. And so we do exactly that. And on the top, you see the actual original image that, or something very, very close to it. It turns out they had an implementation bug that allowed us to actually recover basically the verbatim original images. And so that's what our best possible guess, which is very, very accurate, of the original images is. And on the bottom, you have the images we were able to extract out with the previous attack that I just showed you. And it can be like, it looks pretty perfect. It more or less is. If I flip back and forth between the two pairs of images, you'll notice that they are different in that we haven't actually extracted like a bit for bit copy, but they're really close. And so this particular version of Instahide is not giving privacy. And we can do this for the entire challenge data set that they have. These are just some of the 100 images that were used in the challenge data set. So what's the real conclusion here? So Instahide as an algorithm is not private and doesn't really offer privacy in this encoding scheme. But more interestingly, in our paper, we're actually able to show that no encoding scheme that tries to operate like this could ever be private. We are able to do a very strong reconstruction attack here. And we have some theorems in the paper that are able to show this for much less strong distinguishing attacks. And so the main lesson here is that the kinds of things that we do in one area of security, like I used to do almost exclusively generating adversarial examples, transfers very, very well to these kinds of other attacks on privacy systems, and analyzing these things, especially almost anything in these adversarial games, requires a lot of care. And it's very easy to construct systems that upon first glance look like they should be secure, but only later turns out that with the very careful attack, we're actually able to evade them. So thank you very much, and I'd be happy to take any questions.